Have you ever stared at a problem that just seems impossible? Well, today we're tackling a real mathematical monster, a 13th degree polynomial equation. For the longest time, everyone thought you couldn't solve this thing exactly. But what if I told you there's a new theorem that can just crack it wide open? Not with an approximation, but with the perfect exact answer.
All right, so here's how we're going to break this all down. First, we'll look at the equation itself. Then, we'll see why the old school methods just don't work here. After that, we'll introduce the game-changing new theorem, watch it do its thing, and finally, reveal the solution, which is way more elegant than you think.
Okay, let's just dive right into the hard one. We are up against a beast of an equation.
Now seriously, take a good look at this thing. If someone handed this to you on a test, where would you even start? This is definitely not your standard high school algebra problem.
So this is it, the whole shebang, a 13th degree polynomial. You know, for centuries, a problem like this was basically considered unsolvable in exact terms. There's this thing called Abel's impossibility theorem, which proved there's no magic formula for finding roots of polynomials with a degree of 5 or higher. So for ages, the best mathematicians could do was, well, get close. But that's all about to change.
So, you might be wondering, why can't we just use the methods we already have? Well, for a problem this gnarly, it turns out our traditional tools just aren't sharp enough. And that really is the heart of the problem. You know, methods like Newton's method, they're great for getting you in the right ballpark. But close just doesn't cut it. These methods basically make a guess, check how good it is, then make a slightly better guess. But every step of the way, you can get these tiny rounding errors that add up, and you're never guaranteed to land on the exact value. And this really shows the fundamental difference, right? On one side, you've got methods that are all about educated guesswork to get you into the right neighborhood. But on the other side, with Ezouidi's theorem, you have a precise blueprint that leads you directly to the exact street address, completely bypassing the old limits that held math back for so long. So, it's time to bring in the hero of our story. And this isn't just some new trick, it's a totally new way of thinking about the problem. One that promises absolute precision, where we used to have to settle for good enough. So what is Ezouidi's theorem? Well, think of it as a step-by-step recipe. It breaks down the polynomial and solves for its roots symbolically. And that just means it finds the answer using algebra, not just decimal points. There's no guessing, no rounding errors, just pure exact math. Okay, I know what you're thinking. This looks intense. But stick with me here, it's not as scary as it looks. This formula is the engine that makes the whole thing work. The key word is recursive, which just means it uses its own previous results to figure out the next step, building the solution piece by piece. Let's quickly peek under the hood. You can think of each of these parts like a gear in a machine. They all have a very specific job. The formula uses these parts to calculate a whole new set of symbolic coefficients. And these new coefficients are the key. They're going to help us rewrite that original monster polynomial into something much, much simpler. It's a system where every single calculation leads logically to the next, straight to the solution. All right, enough theory. Let's put this thing to the test. Let's apply this formula to our polynomial and see what happens when we follow the blueprint step by step. So, the game plan is super methodical. We're going to use that recursive formula to calculate a whole new set of coefficients. We'll just call them S values. We'll calculate them one by one, from S0 all the way up to S12, plugging in the numbers from our original equation at each step. Okay, so we run the calculation for our very first symbolic coefficient, and bam, the result is exactly 0. Interesting. Okay, let's calculate the second coefficient, and what do you know? It's also 0. You see where this is going, right? The third coefficient, you guessed it, 0 again. And no, this is not a coincidence. As we carefully work our way through the theorem, this amazing pattern emerges.
Every single one of these symbolic coefficients from k equals 0 all the way to k equals 12 turns out to be exactly 0.
Okay, so we've got a whole lot of zeros. What in the world does that mean for our crazy complicated equation we started with?
And this is where the magic happens. Because all those new coefficients we calculated are 0, they basically cancel everything out. The entire intimidating 13th degree polynomial just collapses into this beautifully simple form.
And just like that, the theorem lays it all bare. From this super simple form, the answer is just staring us in the face. The exact root of the equation is x equals 1, and it's a root that's repeated 13 times. No guesswork, no error margins, a perfect symbolic solution. So what's the big takeaway here? At the end of the day, this theorem offers a path to certainty. And in fields like orbital mechanics or financial modeling, places where these high-degree polynomials pop up, having a way to get the exact answer instead of just a pretty good guess, well, that's a total game changer. And that kind of leads us with this final big thought. A problem that was considered mathematically unsolvable for centuries just got taken down by a brand new way of thinking. It really makes you wonder, doesn't it? What other huge challenges out there in science and technology aren't actually impossible? They're just waiting for their own new theorem to come along.